For generations, the Big Bang has been our answer to the universe's origin. A universe born from a singularity, expanding and cooling into everything we see today. This idea has shaped not only our scientific understanding, but also our imagination, inspiring countless theories, experiments, and even works of art. The notion that everything, space, time, matter, emerged from a single, infinitely dense point has become a cornerstone of modern cosmology. But science thrives on questioning even its most cherished ideas. The spirit of discovery is fueled by curiosity and skepticism, pushing us to probe deeper, to challenge what we think we know, and to search for answers beyond the obvious. The Big Bang Theory, despite its successes, leaves us with puzzles like the singularity, where physics breaks down, and the need for inflation, a hypothetical fix. There are lingering mysteries. What came before the Big Bang? Why did the universe inflate so rapidly in its earliest moments? And what exactly triggered this cosmic event? These questions remind us that our current models, as powerful as they are, might not tell the whole story. What if the universe didn't begin with a bang at all? What if the true story of our cosmos is even more subtle and profound than we ever imagined? Researchers at the University of Barcelona and the University of Padua propose a radical alternative, a universe emerging smoothly from a pre-existing state, not from a violent explosion. Their work suggests that the cosmos may have transitioned gently from a timeless quantum realm, sidestepping the need for a singularity or a sudden explosive birth. In this new vision, the universe's birth is not a dramatic event, but a graceful unfolding, an evolution from a quantum landscape where time and space themselves gradually take shape. This approach could resolve some of the deepest paradoxes in cosmology, offering a more complete picture of our origins. This isn't just a tweak, it's a new first chapter for the cosmos, inviting us to rethink everything about our beginnings. It challenges us to reconsider what we mean by beginning, and to explore the possibility that the universe's story is richer and more nuanced than a single explosive moment. Imagine a cosmos born not from chaos, but from the subtle hum of quantum reality, where the grand structures we see are the result of gentle ripples in spacetime. In this scenario, the seeds of galaxies and stars are sown by the faintest fluctuations, echoing through the fabric of the universe. Scientific progress means daring to look beyond the familiar, to ask new questions, and to follow the evidence, even if it leads us far beyond the echo of a Big Bang. As we peer deeper into the cosmos, we may find that the universe's true origin is even more wondrous and mysterious than we ever dreamed. If there was no bang, what was there? What if the universe didn't begin with a violent explosion, but with something far more subtle and mysterious? The new theory suggests our universe began its expansion from a de Sitter space, a vast, empty expanse filled with dark energy. Imagine a realm where space itself is gently stretching, driven by a mysterious force that permeates everything, even in the absence of matter or light. Unlike a singularity, de Sitter space is a stable, expanding state described by Einstein's equations, matching the accelerating expansion we observe today. Instead of a point of infinite density, it's a smooth, ever-growing fabric, echoing the universe's current behavior. There's no moment of creation from nothing, just a transition from this calm, empty state into a universe filled with matter and structure. The cosmos doesn't burst forth. It unfolds, gradually giving rise to the galaxies, stars, and planets we see today. Picture a calm ocean, not a volcanic eruption. The de Sitter beginning is tranquil, like the surface of water before the first ripples appear. The universe emerges from gentle swells, not a single explosive event. These swells represent the subtle fluctuations that eventually seed all cosmic structure. The de Sitter model replaces the mystery of the singularity with a well-understood physical state, consistent with current observations. It's a framework that scientists can test, refine, and use to make predictions about the universe's earliest moments. Our universe's accelerating expansion hints that its distant future, and perhaps its past, are both de Sitter spaces, creating a cosmic symmetry. This symmetry suggests a universe that is balanced, with its beginning and end echoing each other across the vastness of time. This theory reframes the beginning as a graceful transition, not a cataclysm. It invites us to see the cosmos as a place of continuity and elegance rather than chaos. It offers an elegant, connected picture of the universe's origin and fate, one where the story of everything is written in the gentle unfolding of space itself, from the quietest beginnings to the farthest future. The beauty of this new model is its simplicity. It needs only two ingredients: gravity, as described by general relativity, and quantum mechanics. Unlike inflation, which relies on hypothetical fields we've never observed, this theory uses only established physics. Quantum mechanics tells us that even empty space is alive with fluctuations, tiny jitters that never truly vanish. In the early de Sitter space, these quantum jitters were enough to kickstart the formation of cosmic structure. No exotic particles, no speculative fields, just the inherent properties of space-time and quantum reality. This minimalist approach is what scientists call elegant, explaining the universe's origin with the fewest assumptions. It's like creating a masterpiece with only the essential tools. The theory bets that the universe's secrets can be unlocked with the physics we already know. How do you get galaxies from an empty, expanding space? What mysterious forces could shape the universe from a void so vast and silent? To answer this, we must journey back to the very beginning, to a time before stars, before atoms, when the universe was a sea of potential. The answer: gravitational waves, born from amplified quantum fluctuations. These are not just ordinary waves, but ripples in the very fabric of space-time itself, carrying the echoes of the universe's earliest moments. In the early de Sitter space, quantum jitters didn't just create virtual particles, they stretched space-time itself. Imagine the universe as a restless ocean, with tiny fluctuations constantly disturbing its surface, each one a spark of possibility. As the universe expanded, some of these ripples were caught and amplified, transforming fleeting quantum effects into lasting gravitational waves. The expansion acted like a cosmic amplifier, turning the smallest tremors into waves that would echo across eternity. Imagine a ripple in a pond that grows as the pond itself expands. Tiny disturbances become mighty waves. The universe's own growth magnified these ripples, allowing them to travel vast distances and shape everything that would come after. These primordial gravitational waves became the architects of the cosmos, carrying energy and momentum across the young universe. They moved unseen, but their influence was profound, setting the stage for the formation of all cosmic structures. They subtly compressed and rarefied regions of space, laying down a blueprint for where matter would gather. These patterns, invisible to the eye, determined the locations of future galaxies, stars, and planets. Even in a nearly empty universe, these waves created the seeds of future complexity. The faintest ripples became the foundation for the cosmic web, the intricate network that would one day connect all matter. The invisible scaffolding of the cosmos was set by these early ripples. Like the framework of a grand cathedral, they provided structure and order to what would otherwise be chaos. From quantum whispers, the universe's grand structures began to take shape. What started as the faintest tremors in the void became the galaxies, stars, and planets we see today, a testament to the power of gravitational waves at the dawn of time. The next step: turning gravitational waves into matter. According to Einstein, energy and mass are interchangeable. The energy in these primordial waves could have decayed into a hot soup of fundamental particles, quarks, electrons, and more. The process wasn't uniform. Stronger waves meant denser regions, weaker waves meant emptier ones. These tiny differences, just 1 part in 100,000, were enough for gravity to get to work. Over billions of years, denser regions pulled in more matter, growing into clouds, then stars, then galaxies. Galaxies clustered along the original pattern set by the waves, forming the cosmic web we see today. Vast voids emerged where the waves were weakest. The universe's structure is a direct map of those first gravitational ripples. A theory must make testable predictions. This new model does just that. It predicts a specific spectrum of primordial gravitational waves, a unique signature different from standard inflationary models. To detect this cosmic song, we'll need next-generation observatories like LISA, or experiments that search for imprints on the cosmic microwave background. If we find a gravitational wave background matching this prediction, it would be strong evidence for the theory. The model also predicts subtle statistical features in the large-scale structure of galaxies, features we can map with telescopes like Euclid and the Rubin Observatory. If the seeds were gravitational waves from de Sitter space, the galaxy distribution should reveal it. The universe holds the clues, we're building the tools to find them. This is science at its best, bold ideas, put to the test by observation. In physics, elegance means explaining the most with the least. This new model is a stunning example. It resists adding new unproven ingredients, relying only on gravity and quantum mechanics. Occam's razor says the simplest explanation is often best. This theory embodies that principle. Complexity, from galaxies to life, emerges naturally from a few simple rules acting over vast time and space. The universe doesn't need a complicated instruction manual. Its potential was always encoded in the laws of physics. This vision is more awe-inspiring than any miraculous event, a self-organizing cosmos, inevitable from its basic ingredients. The beauty lies in the idea that the entire sweep of cosmic history was written in the fabric of space-time itself. Uniting general relativity and quantum mechanics, theories of the large and the small, has been physics' greatest challenge. This new model operates at their intersection, using quantum fluctuations and expanding space-time as partners in cosmic creation. It offers a concrete scenario where quantum phenomena have large-scale gravitational effects. If correct, it would mean the cosmic web of galaxies is a quantum phenomenon on the grandest scale. Cosmology becomes a laboratory for quantum gravity, with the universe itself as the experiment. Instead of smashing particles, we look to the sky for clues. This theory could be a roadmap to a deeper understanding of reality itself. Science is an endless journey into the unknown. Every new theory opens more questions than it answers. This proposal is bold and creative, challenging old ideas and pushing the boundaries of knowledge. Soon, new detectors and telescopes will gather data to test these ideas, listening for primordial gravitational waves, mapping galaxies in detail. For the first time, we may empirically distinguish between different models of our cosmic birth. Theories rise and fall by the evidence, not popularity. Our quest to understand the universe's origin is deeply human, a testament to our curiosity and drive to comprehend the cosmos. The frontier is endless, and the exploration has just begun.